Okay, good afternoon. Thank you for coming today. I'd like to welcome you to the kickoff event for the Society of Petroleum Engineers here at BYU. My name is Jess Carlson. I'm the chemical engineering representative for our local SPE chapter. I'd like to welcome the students of the local chapter and guests, as well as the students from the University of Utah chapter and the Salt Lake National chapter. And I'd like to thank you for joining us in this exciting opportunity to listen to a distinguished faculty member as he discusses the careers in petroleum engineering, as well as his research in reservoir engineering, and a little bit of information about Dr. Hales. Hugh Hales joined BYU's Chemical Engineering Department in 1995 as a research professor. He was previously employed by Exxon and Mobil oil companies, and as an assistant professor of chemical engineering at the Massachusetts Institute of Technology. His research interests are in the area of petroleum engineering, particularly reservoir simulation, which is a computer simulation of the flows of oil, gas, and water through subterranean oil reservoirs. He has taught several classes at BYU, including 263, problem-solving techniques for chemical engineers, and 541, computer design methods, which parallel his research interests. With that introduction, please join me in welcoming Dr. Hugh Hale.
Thank you very much for this opportunity to be here. This opportunity comes because I'll be leaving BYU in the next few days or weeks, and I'm really appreciative of the SPE for inviting me to give this last lecture concerning my research work. I had in mind that I would talk more about careers in petroleum engineering, which is more philosophical. The older you get, the more philosophical you get and the less technical oriented you get. And so it was really appealing to give you all these bent up feelings that I have about careers in petroleum engineering. But Dr. Hengren asked me to talk about my research in reservoir simulation. And that's because he's invited me to collaborate with him in doing research at BYU and continue this work that I've been doing for the last 18 years. So the talk will be like this: careers in petroleum engineering, which includes entry-level petroleum engineering jobs. And I'll give you some counsel on how to succeed in petroleum engineering careers. Actually, the counsel I'll give you I don't think is restricted to petroleum engineering, but that's been the extent of my career. I don't know anything about anything else, so it applies particularly to petroleum engineering. And then to talk about reservoir simulation, which is my research forte, and take some time to do that. But this is going to take the majority of my enthusiasm, and hopefully we'll get down here to talk about research at BYU. But let me just say that I invite you to join Dr. Hedgren and I in furthering this research in reservoir simulation, and hopefully by the end of the hour you'll know what reservoir simulation is. So if you're interested in a career in petroleum engineering, and probably you wouldn't be here if you weren't, you might expect to get a job doing as a drilling engineer, a completion engineer, a pipeline engineer, an operations engineer, or a reservoir engineer as you graduate. And all of these positions work together and collaborate on the production of oil out of oil reservoirs. They're called a reservoir management team. Not all reservoirs have all these members of the team, depending upon their level of maturity. If they're a new field, they will have more people than if they're an old field. Every field has a reservoir engineer associated with it, and I was a production engineer for a time, an operations engineer, and a reservoir engineer in the field. And when I was out there, I would have about 10, 15 fields that were that I was associated to, but one or two would take up all of my time. So that's what you can expect. Now there are other people that are involved in the reservoir management team, which are not engineers, and they include geologists, geophysicists, and paleontologists, and we'll talk about all of these activities because they are all intertwined to make the team work effectively. So I want to talk to you about success in petroleum engineering. First is to get a job in one of those areas, and to begin your work in the reservoir management team to produce oil out of the ground. But as soon as you get that job, then that's a mission completed, and you want to know what do I need to do to be successful in that career. And that's where I suspect my advice is unique. This is not going to be advice that you've heard before over and over again, and you can just sit back and kind of close your eyes. This is going to maybe surprise you. Well, in order to decide what you need to be successful in petroleum engineering, you need to decide what is success. What do you want to do? What success varies. When I teach 391, I ask you to make some goals, and some of you have been in my 391 class and set goals. That means you're defining what you think success is. I would submit to you that success is being able to serve your fellow men. We come to BYU to learn and to go forth to serve. To serve people is the object of our life. That's what we would like to do. So how can you know what service is important and what service is less important? There are all kinds of things you can do. You need to serve your children, you need to serve your spouse, you need to serve your family, you need to serve your neighbors, you need to serve your ward members. But engineers are particularly unique in that they can serve all the people of the world. And that's really powerful. So that's what you might shoot for. Something that will be a benefit to all mankind, would be a great service to your fellow men. So how can you know if your service is worthwhile? I would submit to you, you just look at your paycheck. Now you might say that is a little bit monetary, a little bit worldly, but I submit to you that if you operate for an oil company or anything else that has a free market, has capitalism, then you're going to get paid commensurate to how much you serve your fellow man. You get rewarded for that. That's how the system works. And so you can expect to get paid for what services you do to your fellow man, and your paycheck may be a good monitor of that. Now that only works in capitalism. It doesn't work in all the things that you might do, and you might go to work in a position that doesn't have that kind of reward system. And that includes a place like BYU. You don't know from what you get paid whether you're successful or not. And that's been a big dilemma since I've been here, and was used to getting a big paycheck, and now I wonder, am I doing any good? So I submit to you that you have to weigh. One way of knowing whether you're doing any good is to look at the student reviews. And did they praise you? And another way to learn if you're doing anything is to look and see if your students are learning anything. Now, you really get to learn something if your teacher stresses you. If he really demands things of you, you'll learn a lot more than if he just takes it easy. So that's the dilemma that I have faced, and all the professors face at the same time. Do you really want to make the class enjoyable, or do you want to make it something that they'll learn as much as they can? And so that's the problem. But most of you won't. If you go into industry, you won't face that kind of thing, and you will know by looking at your paycheck if you are doing any good. So how can we go about making a lot of money? How do you do that? Well, first of all, you might demonstrate your technical excellence. And we train you to do that here at Brigham Young. We give you a good background in engineering. Whatever discipline of engineering you're in, we strive to do that, and we do a good job. That's what education is all about. But there's another aspect of that which is really important too. You need to demonstrate some leadership. And I suspect in terms of your paycheck, the most remunerative exercise you will have is demonstrating leadership. They pay more for leadership than they do for technical excellence. But they pay most of all if you have both of them and can contribute in both of those areas. Leadership is a lot harder to learn. It's not something that we teach. Well, we do teach leadership in at BYU. In fact, there's a class called Moral Leadership, 231, Engineering Technology 231. I taught that class. I had a very difficult time teaching leadership. I'll talk more about that. But how do how do you learn leadership if you can't take a class in leadership? And I would submit to you that you just practice, practice, practice. And that leadership is not a science, is not something you learn like engineering, it's an art. And you'll learn to be a leader just the same way you would learn to be a pianist. You sit down at the piano and you play and you play and you play until you master those skills. Now the skills of an artist are very different than the skills of an engineer because, I don't know, the brain just engages differently. You learn, you don't, well, I don't even know how to explain the differences, but you know the differences, and the fact that you're here suggests that you have this ability to be an engineer, to think through the solution and not just have it spontaneously burst forth because you have done this so many times. So perhaps most of you are better engineers than you are leaders, because it takes different skill sets. But I submit to you that you need to be both. You need to be both an engineer, you need to be both a scientist and a leader, an artist. So how can you get these leadership opportunities? You could take Engineering Technology 231 and they would talk to you about that. Actually, you could go down to the business school and get an MBA, and they would teach you a lot about leadership and in particular management, business management. But that's not the best exercise. You can get leadership opportunities by having a record of successes. You just go, you start at the bottom, you do a good job, you do another good job, and you do another good job, and pretty soon people are looking to you to do a good job. That's how professors become leaders. That's how people that are outside of the capitalism get a good job. In some instances, particular legislators are those kind of people. You set a track record and people consider you a record. The problem with that is as soon as you mess up, you're no longer a leader. Whew, forget about him. The other way is to do that by appointment. That's the easiest way to become a leader. Somebody said, okay, you're the leader, do it. And that happens all the time outside of academia and outside of the legislature. And people become appointed, designated leaders, designated managers, designated presidents, even designated bishops. How many of you are appointed leaders? Nobody? Oh, a couple, a few. You're just afraid to admit it. I remember when I became president of the Deacons Quorum, I thought, oh, this is a farce. I'm not a leader. I just have to sit here and listen to the advisor, and he does everything. And I missed the boat. But as I had further leadership opportunities in church, particularly when I was 32, I became a bishop. And I thought, uh-oh, this is really leadership. What am I going to do here? I got to go to leadership. I got to go to the Bishop's Training Center and get some training. But there was no Bishop's Training Center. I had to go to Salt Lake and get some counsel from the General Authority. Back in 1972, there were no, the stake presidents didn't have authority to set apart bishops, and they all came to Salt Lake. And I got a 30-minute interview with Elder Joseph Anderson, and he told me how to be a bishop. And his counsel was, number one, hold confidences. If members tell you things that are confidential, you don't tell anybody. You don't tell anybody. And number two is be transparent. Don't try to be keep secrets from your congregation. Be as open to them as you can. So these two bits of advice I've lived with all the time, and you know they're a little bit contradictory, but I remember them. They're good advice. They're good advice to you in whatever leadership capacity you get in. But I'd been watching bishops all of my life, and I knew what they did, and so I emulated the bishops, and I knew what they did. That was, they enabled people to reach their goal. They tried to eliminate all the barriers that people had to reach their goals, and the goals that he wanted to enable was exaltation, celestial kingdom. So that, in a nutshell, is what a bishop does, and that was a pretty easy, just based on that premises, to be a bishop. So the question is, can I get leadership experiences while at BYU? Does taking 231 or an MBA, does that help you at all? And I would say, yes, it is. But when I took 231, I thought, here's an opportunity to go forth and to give these students some real leadership training. And I gave them many assignments during the course of the semester to work as a team, to work as a team with a designated leader and do some projects. And we started out the first day, and I interviewed the class really briefly and found a leader, because what we were going to do was to make a symphony of a piece that they'd never heard of, although it was out of the hymn book and we had lots of copies. And they were to do the symphony on kazoos. So we practiced. We got a leader. We got leaders for each of the sections of the kazoos, and that went off like magic. I could not imagine the great leadership that was displayed in making this symphony of kazoos. Nobody, of course, had ever played a kazoo before. And I thought, this is going to be a magnificent semester. We're going to really do some leadership things that are great. But then when I had several teams, and they were pitted against each other. Who's going to do the best job? And your grade's going to depend upon that. When I said that, all thoughts of leadership went down the drain. The people couldn't imagine having a leader where the leader was going to control their grade. They're in charge of their grade, and they wouldn't take anything else. The answer, my answer is no. No, at least not in the classroom, because grades are too important to students. They won't follow the lead of their leader, their designated leader, if they think they're going to get a bad grade. So people get put into teams, as you have been at BYU and in high school and in junior high and all through school, and you get in a team and you kind of function by everybody does a little bit of the task, and pretty soon a leader emerges because he's done the best job and he's doing the things and kind of directs what's going on. But more than anything, he just does the work because he had the best idea, and you accept his work and try to help him, and the rest of the team just sits back and relaxes. That's not a team, dear brothers and sisters, or ladies and gentlemen. This is BYU. We got some other listeners, though, coming in here. That's not a team. You need to honor your manager and don't try to run right over him. The main thing I could tell you is don't work in a team as you have at BYU when you graduate, or you will get no place. You run over your manager, he will delegate you to outer Siberia. I don't know where, but you won't be successful. So the training that you get in teams is not going to work for leadership. It does not promote leadership. And another thing is the pace is too fast. To become a good leader, you need to build up rapport with your group. You need to get some respect with them. Now, when I became a bishop, was 4 years before I became a manager, which was really nice, because by the time I had been a bishop for 4 years, I knew how to be a manager. I said, I'll just do what I did with the bishop. But instead of enabling their exaltation, I enabled them to make a profit for the company. And that's what they need to do. If you're going to be successful in a role other than leadership, you need to make a profit for your company. You need to look to your manager to enable you to do that. Now, the manager, of course, wants to make a profit for the company too, but I have found, and I sincerely believe, that if you look to your people and you try to enable them to do their very best job and make things easy for them, they'll look to you with great respect and love and do much better job than they would do if you had another philosophy. Now, you think, well, I'm a manager in Mobil Exxon. I can pay these guys. They're going to work for me because I give them a raise. That's not true, particularly when they get to a certain level, the level of engineers in particular. You make a lot of money, you make enough money to be comfortable, you're not motivated by a bigger salary. It just doesn't work. So you got to motivate them in another way. And if you're an engineering manager, if you're a technical manager, you're going to do that. If you want to be successful, You use the same method you would with a bishop, of enabling them by making them feel that they can do the job and that you're on their side. You're working to make their life easier. And if you do that, they will do most anything for you, where just to do it for a paycheck, they won't do it. So how do you get leadership experiences while you're at BYU? You've got to do this in another way, like through church callings or working outside of BYU in other employment opportunities. You got to get a real life job. Now, you may have thought, well, I'm here to go to school. That's what I'm going to concentrate on. And you may have outside employment because you need the money. And some of you have church callings because you feel that's your obligation. But I would encourage you to think of these opportunities as real part of your education. This is where you're going to get your leadership training. It's not going to be in the classrooms at BYU. So if you'll face your church callings and your outside employments as part of your education, that will work out well. Okay, this concludes the part one of my talk about petroleum engineering careers, and I'd be glad to get some questions. Anybody got any questions or comments? I don't know whether you're buying or whether you thought that was a bunch of baloney. So I'll move on anyway. We'll talk about reservoir simulation, which is my research research interest.
We have one question.
Yeah, okay. Dr. Bundy.
In your experience, you've observed a lot of students. You've seen a lot of students over your time here. And you've seen what attributes you see in students that really help them be a leader? Help them stand out as a leader?
Oh, that's a really good thing and a good question. I don't know that this is true of everybody, but leadership arises when there's stress. So everybody can be a good leader if you're just sitting back and learning to play the kazoo. That works easily. But if you really have to do something of great significance and it's at all controversial, you could go one way or another, then some leaders shrink. And so those people who will step forth and express themselves at times when there is a controversy are the leaders that I see in among society, including the people at BYU. Dr. Baxter.
Following up on that, do you make a distinction between leadership, management, popularity? Can you talk about
Leadership and management. Management is part of leadership. As I pointed out, there are two types of leadership, and management is one of them. Management is the appointed type of leader, and so that's the distinction. But I think management is every bit as much a leader as a politician is a leader. You can get your appointment, but you can get your leadership capabilities by appointment or by mandate of the people. And what was the other part of your question? What I'm comparing? Popularity. Well, mass popularity is not leadership, but popularity among your subordinates, the people who work close to you, is very important in leadership. So it depends on how big a circle you want to make popularity. Popularity is important to the people you're working with. Anything else about, yeah?
You listed those positions in reservoir careers at the very front.
Mm-hmm.
Talk about what each of those do.
Oh, thank you.
Yeah, that one.
Okay, so, well, this is kind of going to fall into reservoir simulation, but because we need to know about all these things for reservoir simulation. But in order to have an oil field, you need to have some wells. You only get oil out of the ground if you have a well, and that's what a drilling engineer does. He engineers the well. He's out there, he designs it, and he contracts to get it drilled. Oil companies don't drill their own wells. There are drilling companies, and they come in and drill to whatever specifications that you have. The completion engineer is the person who makes the reservoir, the underground accumulation of oil, flow into the well. that's going to be at some depth, and we put down this steel pipe down there, and there's no way the oil can get down there unless it's so-called completed, and that is to punch a hole in it. You actually fire a hole into it. You use some plasmas, which are anti-tank weapons, and you burst a hole into the pipe and out into the reservoir. That's the type of engineering that the completion engineer does. Then once we get the oil to the surface, we have to take it someplace, even if it's just a few hundred yards to a storage tank, which is going to be hauled away by a truck every few hours. But today's oil fields are so big that you have a pipeline which accumulates over lots of acres, lots of miles, and then goes into a major pipeline. That's that pipeline's job. And then there are operations engineers. This is much like what people do in refineries. They're called operations people, and they make sure everything works. Everything's going well. They go out, if they're pumping wells or whatever the equipment is, they make sure they're working well, and if they need to be improved in design, that's what the engineer would do. The reservoir engineer is in charge of optimizing the amount of oil, the profitability of the reservoir, which means he has to combine all of these things. So the reservoir engineer is the head of the reservoir management team, all just by nature, because he has the most insight into what's going on. And the geologists, of course, try to describe the reservoir. What's the geology like? What are the layers? What are the strata? What are the permeabilities? What are the porosities? Geophysicists are in charge of gathering that type of data. That's done by seismic analysis, which I'll talk to you more about. And paleontologists look into the fossils that are in the rock. Now you might find that surprising, but there are fossils in all kinds of rock. There aren't dinosaur bones in all kinds of rock, but about any rock that you pick up that is not igneous, that has not been under fire, will have some fossils in it, mostly of microscopic size, a microscopic type of animals, but they're nevertheless distinct. So the paleontologist looks at the rock and identifies the animals which describe the dispositional environment which the reservoir was laid down, which affects the properties. I'll get into that if I have enough time, but that's the type of people who make up the reservoir team and the people that you might be involved with. So a reservoir simulator is a computer program that simulates, that virtually depletes the petroleum-containing reservoirs. That is to say, we get all the data from what might arise from depleting the reservoir, but it really didn't get depleted. It's imaginary. We used to use the word imaginary, but now, because computers do it, it's called virtually. So what does the reservoir look like that we're going to simulate? Well, I have some pieces of reservoirs here. Reservoirs are non-igneous rocks, and generally sandstone or limestone. This is a limestone. This happens to be out of the largest reservoir in the world. And you might imagine that's in Saudi Arabia. It's called Ghawar. I used to have a lot of these cores, but gradually I've lost them. This is my only remaining core of Ghawar. I was in Saudi Arabia for several years and collected these things, but you can see where there are pores in this rock. You can really see them, little holes, but no gigantic caves. That just doesn't happen. The rock is contained in the pores of the rock, which are visible in this rock. So if you'd like to pass that around, you can examine what a core really looks like. Now, most reservoirs are more like this one, which comes out of West Texas. This is from the Permian Basin, and this rock looks like it's solid rock. In fact, you look at this and you think it looks just like my granite surface on my countertop, which is on my countertop because it's impermeable. But this is not impermeable, it's just polished on one side. So if you look at, because it's a bookend, but on this side it's a native rock, and you can see it's rock and it's got some pores in. They're just very tiny. So that's a reservoir. The reservoirs are just rocks that have oil in them, and they're not particularly special except for the fact that they have rock. They're certainly not special because they're caves and have big holes in them. So we know what a reservoir is now, and we want to use our reservoir simulation to predict how much oil is going to flow through those rocks. Repeated simulations allow reservoir engineers to optimize production and profitability. That's what it's all about, getting the most oil out of the ground and hence making the most money. A reservoir simulator calculates the underground flow of oil, gas, and water, at least. We generally have those three phases that we calculate. It predicts the changing pressures and saturations throughout the reservoir, and sometimes also calculates, in addition to oil, gas, and water flows, it calculates the chemical composition and temperatures. That is, we get various molecules, methane for example, moving out of the gas phase into the liquid phase and back and forth depending upon the pressure. That's called the compositional model, and complicates it considerably. So most reservoir simulators are called black oil simulators because they consider only gas, oil, and water. Gas is just one component. Oil is just one component. A reservoir simulator solves partial differential equations, and we'll talk more if we have time. These are complicated equations, and we're going to use a computer to do that, and it takes a really lot of time, and that's why this research is exciting, because of the complexities of solving those equations. Generally, we use the finite difference method, and I think that's done 100% of the time in commercial applications and 100% of the time in the research that I've been doing. Large amounts of data are required, as you can imagine, to describe the reservoir. These data consist of geometry. We have to know what the reservoir looks like. Well, you have some pieces around. How do you describe the geometry of those rocks? Porosity, permeability, relative permeabilities, and fluid properties. And those are the most important parts of the data. So we want to start out by describing the geometry. The geometry of the reservoir occurs because the oil is lighter than the water in general, and it tries to seep to the top of the earth, over the top of the water, to percolate through, but it gets trapped somehow. And it gets trapped because we have a permeable layer here, which was a strata laid down in some environmental environment, and an overlying layer which was set down in more harsh conditions and has a zero permeability. So this might be shale. Shale effectively has a zero permeability, very small, and so the oil gets trapped in this area, and that would be called an anticline. It's just the top of a hill. The hill is submerged in the earth, and the oil rose to the top. We can also have stratigraphic traps where the oil rises, but the permeable layer pinches out. It no longer exists, so it just goes as high as it can and sits there until somebody drills a well in it. The most widely found method of deposition is to have a fault. You have the reservoir impermeable. This layer can't let the oil flow to the surface because there was a fault here, and the earth shifted, and so the layer which was down once adjacent to this one now is down here, and it can't make it through the fracture. Now you might find that strange because fractures are breaks in the rock. You would think that would have the greatest permeability, the greatest way to flow as possible, but it turns out that if a fracture is of any age, and we're talking about thousands if not millions of years, the fracture gets cemented. That is the water that's percolating up here, and it percolates up because it has a temperature gradient. The water, as we go deeper in the earth, it gets warmer and warmer, and it comes up and it gets cooler, and when it does so, the salts in it, the minerals come out of solution and plug the crack. And they can do that as sediment much more tightly than the sitting down of the sand grains to begin with, and hence we get a very impermeable crack rather than a permeable crack. Now, how do we know where these mountains and hills are in the earth if they're covered up? And they're not always evident from the surface because erosion wipes out the top of the mountains up here on the surface of the earth. So we've got all of these hills under the ground, and we'd like to know what they look like. This is the area of geologists called seismography. And what happens in seismography is you send out a big noise up at the top of the earth, and it comes down to the various layers and bounces back. It's an echo. It just echoes back off each of the layers, and we record those echoes. They don't last for more than 2 or 3 seconds, and they've died down, but we take an enormous amount of data in those 2 or 3 seconds and go back to the computer room and try to solve the wave equations to match up the properties and distances of these various echoes that come back. So what do you think is the property of the reservoir which causes echoes? As I'm talking, my voice is echoing back off of that wall, although it comes back so fast it doesn't disturb you. But you know what echoes are. It takes if it's a long way, you can hear them. What property causes the echo to come back?
Is it the change in the density of the rock?
Well, yes, it is. Good answer. It's really a change in the derivative of the pressure, the derivative of the density with respect to pressure. That's called compressibility. So this wave goes out because I compress the air and I send out a wave of pressure oscillations that go out across the room, and then when it gets over to there, the compressibility of that wall is a lot less than the compressibility of this air, so it comes back. So what we're really measuring, we're mapping when we map the reservoir, is the compressibility, which is likened to the density of the rocks as they as the sound travels into them, and we build the maps in that fashion. Now that takes a lot of computer work, and we used to just set off a line of charges and get back a line of answers, and we would do this in one dimension. Actually it'd be 2 dimension, including the vertical dimension. But now we can do 3D seismography and get models that look like this. This actually is a reservoir simulation model, which means it's a geological model that's been divided up into cells. That's what we're going to do to solve the equations, is to divide our model into cells. That's called the finite difference method. And in this reservoir, we have about 30 layers, and we have about 30 by 30 cells in each dimension. So we would have 30,000 cells or thereabouts in this model, which makes it a fairly small model. You're imagining in each of these cells we have to put in a permeability and a porosity. That is, we have to put properties of the rock, and the rocks are not homogeneous. They're very heterogeneous. As you look at them and they're passed around, you can just see on the relatively small cores that we need a lot of cells in order to do an accurate job of describing the heterogeneities of the rock. So we divide up into a lot of cells, typically more than 30,000. More typical model is 1 million cells. Now we also have to describe the wells, and this is the bailiwick not only of the simulation engineer, but the drilling engineer. The drilling engineer designs the wells, which are then created by a drilling rig. This drilling rig is 120 feet high. That man right there is a man. So you can see that there are enormous machines, and they drill the well by turning the floor of the drilling rig, and that rotates the pipe, and on the bottom of the pipe there is a drill bit, and by rotating it, it's just like a bracing bit, you turn that and it drills into the earth. Now the drills don't last very long. You know, you run a drill into cement, it doesn't last very long if you want to measure in terms of miles. So we had to change the bit frequently, and that's called making a trip. So we take this big crane and pull the pipe out 2 sections at a time. So each pipe is 45 feet long, and we pull 2 at a time just to make it faster and lay it down there. The drilling rig is 120 feet high because if we can't undo the pipe at this point, we pull it up to here and try to undo it at the top. Well, we're not undoing it. We're pulling it out and undoing it down here. But we've got a 3-stand pipe rather than the 2-stand pipe because the drill rig is high. Now this is the same thing. This is the drill rig on an offshore platform, and it's 120 feet high too. So you see these things are, the offshore platforms are enormous. But they contain a lot more than the drilling rigs. They contain production equipment because as soon as you complete one well, you're going to drill a lot of wells from the same platform, and you would like to produce some of them before you get them all drilled. So as soon as one well is drilled, you start producing it, and you run it through the separation plant and down the pipeline to be sold or go to the refinery. This is the quarters for the people who run the rig. This is typically done. They're on for 2 weeks and they're off for 2 weeks. So we rotate shifts, and they work for 12-hour days as they're out there. So there are 2 shifts. Some people are sleeping while others are working, and then the new occupant comes into the room, the same room, and so they rent their rooms in. They get their rooms in shifts. Now, if you're an engineer, you'll love to visit the drilling rig. I really love to visit the drilling rig because they really eat well. You can go into the kitchen in the drilling rig anytime and get, just the most great food. And of course, these guys work really hard, so they have big appetites. And if you go out there as an engineer, you're likely to get fat in just a day or two. This red device, and there should be 2 red devices, though one's kind of off the picture there, are the escape modules. If you have an accident out there, you run and jump into one of these things, and as soon as the door is shut, the module automatically drops at a controlled rate. It just doesn't free fall into the sea, but it gets out of there fast and automatically drives away. So that's the safety precautions. This is for the people who were in sleeping, and this is the people that were working, and that's a safety precaution. Now this thing out here is a barge. They run barges out there to take out the food and the pipe and all kinds of facilities, and occasionally they take naive engineers out there, which I was to begin with. They said, you got to go out to the rig and we want you to do such and such. I don't even remember what my job was. This is lots of years ago. And you catch the barge at 4 o'clock in the morning, and it's going to be a 3-hour trip to get out there to the drilling rig, and then you do your work. Well, when I got out there, there's no stairs. There's no way to get from the barge to the platform. So they take this crane and they lower a seat down, and you're supposed to get on the seat, and it hoists you up to the platform. I'm a little bit acrophobic, and so that was no fun. I still remember that vividly, but that was kind of a hazing prank they pulled on me to begin with, and you don't really do that very often. I only did it once, and there are other times you take a helicopter out there, and it's a much more pleasant and short ride.
Was it a Billy Pew?
Well, I'm sorry?
Did they put you in the Billy Pew? Is that it?
I don't know what the Billy Pew is.
That's the thing so they just lifted you with the crane, though?
Yeah.
That first time? Okay.
Uh-huh. So this is more modern technology. This is more costly, but does a better job of drilling. You can drill a more precise well if you have a flexible pipe. That is, you can guide it. If you got a pill like a drill bit and you just turn the top of it and see where the drill goes, that's not very precise. But if you can bend it and make the drill go in various directions on the very bottom, it's navigated and can go at angles, then you get a much more precise well and a much more profitable well. So this kind of drilling, which is called flexible tube drilling, it doesn't have a steel pipe on it, is very popular in remote areas where they can afford to do more expensive things. For example, on the North Slope. In Alaska, they use this almost exclusively, and the drilling string then goes down. It goes down and is guided and can turn and go along the strata. So if we got a strata down here that contains the oil, and if we drilled a straight well, which is the old-fashioned type, we'd have contact with the reservoir for its width, which may be several hundred feet, but still not much compared to the lateral length of the reservoir. So we make a turn. We drive the drill bit right down the strata containing the oil. And this makes oil wells much more productive. So much so that we now drill in shale. And that's been an industry which has revolutionized the petroleum industry in very late years. It's still a revolution that's going on. We're getting oil out of shale, which is such tight rock that we always considered it impermeable. But it does have rock in it, oil in it. And this is the kind of oil that you get out of it. Now, I don't know that, oh, my time is up. Let me just finish with this oil shale business. This is oil shale. It is clear. You get clear oil of that. I don't have a sample of crude oil that comes from normal wells because it's so ugly and gunky and sticky. It just looks like a black. Well, you've seen asphalt. It's the same stuff. So this is oil shale. It gets refined as it's coming out of the rock because the large molecules can't make it out. Only small molecules can make it out. The other interesting thing about this is it's got 4 phases in it. 1, 2, 3, actually 5 phases, including the solid phase and the gas phase at the top. So take a look at that. That's a unique kind of oil and creates great problems, nice technology for people who are doing reservoir simulation because of the fluids have such interesting properties. My time has really flown by, but I'll be glad to answer any questions, or perhaps we need to do it outside of the class, yeah?
That's from South Texas, right? The oil?
Yes. Did you bring that oil to me?
No.
I got that from a student.
It's from the Eagle Ford, right?
Yeah, that's right. Well, that's all I'm going to say to you. Thank you very much.
Okay, so we have time for maybe 1 or 2 more questions.
Okay, great.
And then we'll go ahead. I don't think the class is coming in after this.
Oh, wonderful.
You guys want to
Yeah.
do 1 or 2?
On the drawing when it says not to scale, is it because it should be deeper, or it's exaggerating the height?
Are we talking about the drawing is not to scale? Yeah. I don't know, since it's a schematic anyway, but we can drill out miles in this direction, but on the other hand, we can drill down in miles. So this is 3 miles and this is 3 miles. And a 3-mile well, deep well would be what, 15,000 feet, 12,000 feet. Wells are that deep fairly commonly, so I don't know what they're trying to make other than it's not a scale drawing, it's just a schematic, yeah.
Would you like to give us like a 2-3 minute summary of your research and maybe
Oh,
like where we go if we want
thank you, thank you, thank you. Okay, the research that I'm doing here at BYU has to do with solving linear algebraic equations. We get a set of equations that have an equation for each of the cells in the model. That's what the finite difference generates. We solve the partial differential equations by turning them into linear algebraic sets of equations. But because we want to have 1 million or more cells, we get 1 million or more equations which we want to solve simultaneously. So that's a big part of the research that's going on now to make a fast solver. How do you solve 1 million or even 1 billion linear algebraic equations simultaneously? And that's what we're working on. Characteristic solutions. Now, finite difference solutions are not the only way to solve these partial differential equations, and there's another method called characteristic solutions, which is particularly nice for solving for the saturations. The saturation equations are hyperbolic rather than elliptical, and so they lend themselves to other types of solutions, and so we're investigating the other types. The other type, which is a characteristic solution, which a lot of other people are doing currently. Irregular boundary treatment. I'd like to treat the reservoir as if it were Cartesian coordinates. Every cell in there had right angles with it, and had a rectangular face. That makes the equations very easy, and you don't have to describe the geometry. If you've got 1 million cells or 1 billion cells, just describing the geometry if you have irregular cells becomes a problem. So I want to make irregular boundary treatments treatable by Cartesian coordinates. And the other thing that I'd like to do is to work on curvilinear orthogonal gridding. This is a mapping of the coordinate system into some other coordinate system, the mapping of the Cartesian coordinates into a curvilinear coordinates, which matches the size of the reservoir. And that's shown by this thing. So here's the reservoir. These are the faults in it. I want to represent it in Cartesian coordinates like this, but curvilinear coordinates, I can do a good job. I can match the faults exactly and the boundaries. This is a representation of characteristic solution. We have characteristic lines that move through the reservoir. We don't have constant saturation blocks anymore. We move the lines of constant saturation in this solution. And this alludes to where we're going with higher performance solvers. We're actually doing quite a bit better than this. This was done a number of years ago. And we've got this is the computer time consumed, so we would like to have the line as low. Making it little is the alternative. So here are some solutions. This is Ben Hardy did this as a thesis project a number of years ago, and these are the results he got. And then we did a little better, and we got this line, and we're doing even better than that now. Whereas the fastest public domain solver, this was Ben Hardy looked at a lot of them and found this was what they're doing. So we've reduced it really three orders of magnitude. That's 1,000 times faster than the typical public domain algorithms. That's my 3-minute talk about what we're doing for research.
Okay, well, let's thank Dr. Johnson.
Thank you. Thank you for sticking around.